Let's understand tracing. Say you have a problem, your application has crashed. In this case, you will be using a debugger such as GDB, which will allow you to inspect the system state. This GDB will only allow you once the error has been detected. It does not reveal the events leading to the error. It will give you a backtrace, canon BT command. It will give you a backtrace, but backtrace does not have all the information. To understand why this error or event took place, the relevant context needs to be restored. This is where tracing is very useful. Tracing is a process of collecting information on the activity in a working system. With the help of tracing, program execution is recorded during runtime. This allows for later analysis of the trace. Tracing helps developers with information which is useful for debugging. Now you may have a question like, what is the difference between tracing and logging? Logging is also storing information which is used later by developers for debugging. That both are same. The major difference is with tracing, information is very huge. It is in the number of hundreds or thousands. Whereas in case of logging, information is written about higher level events which are less frequent. Examples can be logging into the system, application errors, database transactions. Whereas with tracing, information is written about low level events, all the events which are happening on the system. This is why tracing is very useful for a developer. So tracing finally is a process, or it can be a program which actually collects information or records program execution during runtime. Let's start with tracing in Linux kernel. We'll be looking into ftrace. Ftrace is the official tracer of Linux kernel. It lets you trace Linux kernel function calls, each and every function which is being called in the Linux kernel. It was added in 2.6.31, developed mostly by Steven Rosted. Ftrace name comes from the popular function tracer. So F stands for function, but it also includes many more functionalities like event tracing, MMIO tracing, function graph, etc. So we'll be looking into all those. Why do I need ftrace, or when can I use ftrace? Say you wrote a device driver, you debugged it, you confirm that everything is working fine. Now you have loaded it inside the kernel. Now you found that it's not working as expected, or something is break when you run it. Something has broken when you run it. Now what you will do when you do not have ftrace? You will normally add print case in the each and every function, and then you start removing the module and loading the new module. With the help of ftrace, you do not need to add those print case. You can find out what functions are being called at the kernel level and easily debug the issue. So what can we do using ftrace? We can debug Linux kernel, the kernel modules, etc. We can find out which kernel functions are taking a lot of time, so latencies can be analyzed. We can understand, or we can learn the kernel, because we are now able to know each and every function which is being called in the kernel. So we can observe the flow of Linux kernel, and we can learn how Linux kernel is working. We can trace context switches, so we can have it know when is the scheduler is being invoked, and we can understand when is context switching happening. So a lot of things we can learn using ftrace. So let's get started. Ftrace is enabled in most distributions by default. If it is not enabled, you can activate by going to kernel hackers tracers. For example, I have the Linux source code here. Make menu config. You can go into kernel hacking. You'll be able to see it directly here in tracers. Here you can see the kernel function tracer. If you say question mark, it will give you the function tracer, ftrace. So if your kernel is not enabled with ftrace, you can enable it in the kernel hacking menu. So the minimum kernel configuration which is required for ftrace is config underscore ftrace, which is tracers, config underscore function underscore tracer, kernel function tracer, config function graph tracer for function graph tracer, and this is for tracing max stack. So let's verify whether I have those configuration enabled or not. Important point is it is enabled in most distributions by default. I am using a Ubuntu 20.04. It has already enabled it. So how can I verify it? I can check the configuration. Boot config. I can say uname -r grep for config underscore ftrace, and this is set. Then I can search for config underscore function, and this is also set. Then I can search for config underscore function graph tracer. This is also set. Stack tracer. So you can also verify this before you actually start working on ftrace, whether your ftrace is enabled or not. Okay, we have ftrace enabled. Now there's another way. You can check whether you have tracing directory or not. So it is present in syskernel tracing. So if you check if this is present, this means tracing or ftrace is enabled. So let's check whether we have a tracing directory here or not. So I have this tracing directory present. Now we know that we have ftrace present on my system. So we need to mount the tracefs. Ftrace is present in tracefs. So we need to mount the tracefs. So initially, you will be seeing ftrace is mounted in debugfs. This is very old mechanism. Like if you see old kernels, you will not be seeing syskernel tracing, but you will be seeing syskernel debug tracing. For example, debugfs is syskernel debug. So syskernel debug, you have a folder tracing here. This was how ftrace was present in previous versions. I have tracing here. So this is the folder of ftrace. But nowadays we are using directly a new folder is being created here, tracing, and this is the folder which we use for accessing ftrace files. So ftrace is nothing but a file system. RAMFS, you can think of it as a tracefs. Tracefs is a file system where you have files provided. Similar to procfs, you have files, right? Similarly, you have tracefs for ftrace. In initial days, you used to have it in syskernel debug tracing, but now in newer kernels, it allows you to mount it in syskernel tracing. You can still find files in syskernel debug tracing if you're using an old kernel or newer kernel. So one way is you can use mount command to mount the tracefs at this particular location, or this will not persist after each and every reboot. You need to try again. You need to run this command for each restart of your system. Another way is you update etcfs tab, where you can add this entry and you do not need to run this command each time. Let's run this command. You need sudo permissions and root. You can observe we have the files which allows you to access and control the ftrace. So this is how you can access ftrace. First thing is you need to check you have the valid configuration or not. Once you have the valid configuration, you can mount the tracefs. because ftrace is having a file system, exposes a file system which allows you to control or access the tracing information. We have mounted ftrace, which is tracefs. So you can see a lot of files are present here, and folders are also present. All the operations on these files are performed by using simple commands like echo and cat. We know echo internally calls write system call, cat internally calls read system call. This is done. This is useful because on embedded Linux systems, you have BusyBox, which do not provide all the functionalities, does not expose all the commands, but you will be having echo and cat. So using this, you can still use tracefs in embedded Linux images like Yocto images, buildroot images, etc. ftrace, like printk, is built around smart lockless ring buffer implementation. We have also printk, right, which uses a ring buffer. When you call printk, it writes to a buffer. You have dmessage to read the contents of the buffer. Same case is with ftrace. Ftrace also have a buffer. This buffer stores all the tracing information and it is exposed as a file. You do not have a command like dmessage, but you have a file in tracefs. We have a file known as trace. When you read this file using cat, it will dump the contents of the buffer. Like dmessage, you have this trace file. Let's look into some of the important files in tracefs. First one is available underscore traces. This file will list what all traces are configured. Some of the important traces are NOP. NOP, no operation or no action. This means no tracer is enabled. A function. Function is the most popular tracer. It traces each and every kernel function entry. Then you have function underscore graph, which will trace both functions as well entry as well as exit. This allows you to build a call graph like a C function flow. Then you have BLK, which is block tracer, all the block operations which are happening. Then you have MMIO trace, all the IO operations, port IO, memory mapped IO. This is useful to trace interactions between drivers and hardware. The default tracer when you mount tracefs is nope. Nope means no operation or no tracer. We can verify that. You just need to say cat available tracers will list you what all tracers are being configured. So here you have lot of tracers including whatever is mentioned here. Hardware latency, block tracer, memory mapped IO, function graph, yeah, function and NOP. Now I want to find out what is the current tracer which is running. For that, we need to use this file. Available underscore tracers file will give you what all tracers are available for you to use. Current underscore tracer is a file which will tell you which is the current tracer which is running. So let's say cat current tracer. So default NOP is the tracer, no operation. So currently NOP tracer is configured. I can change it to function or function graph. We'll see how we'll do that. So current underscore tracer, this is the file which will tell you what is the current tracer which is currently running. Available underscore tracer will list you what all tracers are configured. How to enable a tracer? We have seen available underscore tracers will list you what all tracers are configured, and current underscore tracer will give you what is a currently running tracer. Now if I want to enable a different tracer, we know the default tracer is NOP. I want to enable a different tracer. I need to write the name of the tracer into current tracer. So as you can see here, we are using echo command. Like previously we have used cat command. Now we are using echo. So these two commands are used while you're working with ftrace. Very easy, right? You just need to use echo and cat, the most commonly used commands. So how to enable a different tracer? Into say echo name of the tracer into current underscore tracer file. For example, we have different tracers. So available tracers will give you what all tracers are available, and current tracer will give you which is the currently tracer which is running. Now if I want to enable a different tracer, for example, function. So I say echo, the name of the tracer is function. Then I say current underscore tracer. Now the current underscore tracer, let's verify whether the value has changed or not. Cat current underscore tracer. Yes, now you can observe here. Previously we had NOP, no operation tracer. Now we have function tracer, which is the currently running tracer. Now how to check the content of the buffer? We know we have a file trace which will expose or dump the contents of the buffer. Let's do a cat on this file trace. So you can see currently you have a lot of commands being executed. Once you have enabled function tracer, you observe a lot of commands are being called in the kernel. So like this, you can enable a different tracer. For example, if I enable a different tracer, instead of function, I say function underscore graph into current underscore tracer. Now I say cat current tracer, function graph tracer is enabled. Now I say cat trace. You can observe a different format of content is being printed. Previously it was a different, now you can see it's like a C functions, C graph. So you can see a function start, opening brace, closing brace, and in between there are functions being called. So this is function graph. It will give you a tracing in graph. Finally, when I say echo no, this will, so you need to write into current underscore tracer. When I say trace, the contents are gone. So what we have understood now is we can change the tracer by writing the name of the tracer in current underscore tracer. What all tracers are present, we can find out using available underscore tracers. And to see the content of the trace, what all functions are being called, we need to dump the content of the buffer, ftrace buffer, and that buffer content is exposed using a file which is trace, and just saying cat trace will give us that information. For example, now if I say echo function, I cannot use tab here, say function. I have enabled by writing it into current underscore tracer. You can validate. Now I can just say trace and I can look into some of the values. So let's understand the format. The first one is name of the task. What is the name of the task? What is the PID of this task? Which CPU this particular task is running? Then you have some flags which tell you whether IRQs was off, whether there was preemption, whether hard IRQ or soft IRQ set or not. Then you have timestamp. This particular timestamp is in seconds. This is the timestamp since boot. So you have this many seconds from boot. You can verify using uptime, whether this will get same value. Uptime is not given. Or if you say cat proc uptime. Oh, what? This is the same thing, right? 79573 is the same here. And this is the function which is being executed, and this is the parent function. So this is very useful information, very helpful to debug. You have which process calling this function. We know kernel function will be only executed either through a system call on behalf of a user process or on an interrupt. You can observe here we had an interrupt, a pick timer interrupt. It called SMP a pick timer interrupt, and then this particular function is calling this function. Same thing is happening here. Function graph tracer. We have enabled function graph tracer recently, right? So function graph tracer, it is built on top of function tracer. The difference between function graph tracer and function tracer is function tracer will only trace function entry, whereas function graph tracer, it also records the return address. By this, function graph tracer will come to know when a function enters and when a function exits. So function graph tracer, it tracks the entry of the function, exit of the function, execution time, CPU on which it is running. So a lot of information. CPU on which it is running is also being tracked by function tracer. So additionally, it is tracking exit of the function, execution time. So let's enable function graph tracer. So echo, currently we had current tracer is function tracer. I can enable function graph here. Current tracer. My current tracer is function graph now. Let's say now, let's look into the contents, which is the trace file. So trace file is the file which has the tracing buffer content. So let me say head -20. So you can see the format has been changed here. You had a different format here, task CPU timestamp, but you have a different format here. You have a timestamp here, like what time this particular function executed, but you have a duration here. Not very important is you can see the first line contains what is the tracer currently configured. It is function underscore graph here, whereas here it is function. Okay. Now let's understand this. You have a CPU on which this particular function is executing, duration, and the flow. How is the flow being executed? So let's find out some of the important points. So start of the function is denoted with opening bracket, the curly bracket. This means here you can see this is the function started, and closing of the function is being executed by closing bracket. Functions which do not call any other functions simply end with semicolon. They are also called as leaf functions. In this case, this function is not calling any other function. Same case is this. These are leaf functions because they are not calling any other function. And this is a leaf function. And this is the starting of the function. I can say get -40. So this is the starting of the function. This is a leaf function, starting of a new other function, leaf function, and you have this function is closed here, and this function is closed here. And then you have duration here. Duration is only reported for leaf functions and the closing symbol, the closing bracket symbol. So here you can observe here, this is only reported for leaf functions. This function took 0.750 microseconds. Same in case here. So this also being reported for closing brace, curly brace. This means this whole function took 2 microseconds. Like you can calculate, it took 750, 754, 632. When you add, this becomes this. So the duration is mentioned for leaf functions, as well as duration is mentioned for functions or lines which has a closing curly bracket or brace. And whenever the duration is greater than 10 microseconds, plus is shown in the duration column. If it is greater than 100 microseconds, minus is shown. Greater than 1000, hash. So for each and everything, if it is greater than 10 milliseconds, asterisk is shown. 100 milliseconds, its @ is shown. 1 second, $ is shown. Let's try to find out whether we have any functions which are taking lot of time. So let's find out for hash. I'm going to grep for hash. You can see a lot of functions are taking more than 1000 microseconds. So 1000 microseconds, any function which is taking more than 1000 microseconds, we'll be seeing hash here. This doIdeal is taking more than 1000 microseconds. Let's look into @. @ means it is taking 100 milliseconds. So there are some functions which are taking more than 100 milliseconds. For example, this schedule is taking 234 milliseconds. So 234 into 1000. So 234 milliseconds. So using this, you can find out. If I say $, let's say $ is there. $. So there is no $ here. There is no $. Using regular expressions, you can just say grep f. Yeah, there are some dollars as well. So using function graph tracer, you can also find out execution time. And using these symbols, you can find out which functions are taking a lot of time. The content of ftrace, you have observed, it's very large. If you see cat trace, it will be very large. Lot of information. So many lines, of information. And finding exactly what you're looking in this can be extremely difficult. So in this case, you can use filters to simplify our search. When you use filters, trace will only contain information about functions you are interested. So what are the files for filters? You have more files, not two files. First file is available underscore filter underscore functions. So you have this file here. Available underscore filter underscore functions will list you what all functions you can add or you can filter. Let's do a cat. So a lot of functions are present here. This all functions can be filtered. And you can look, so you have like 45,000 functions which are available for filter. Let's do a search for some functions like kfree. Do I have kfree here? Yes, I have kfree here. Do I have kmalloc? Yes, I have kmalloc as well, underscore kmalloc. Do I have VFS functions here? Yes, we have VFS function as well. VFS mknode, VFS create, etc. VFS read. Do I have do underscore IRQ? You know what is do underscore IRQ? The common function is called on every interrupt. So we have do underscore IRQ as well here. So all the functions are available here, like all the common functions are available here. So available underscore filter functions file will give you all the functions that can be filtered or that can be traced. So now if I want to only search for some of the functions, I do not want to search all the functions. Now all these functions are being traced. If you see, all the functions which are present in available filter functions are being traced. I only want to trace few of the functions. In this case, I can use these files set underscore ftrace filter and set underscore ftrace no trace. Set underscore ftrace filter will only trace the functions which you mentioned in this file. Set underscore ftrace underscore no trace will remove those functions. It will not trace these functions. So this is opposite. But if you have information present in both the files, then no trace will take precedence over filter file. So how to use this? Again, use echo. Echo the name of the function in ftrace filter. If you have multiple, then you can separate using commas. And you can also use append operation. When you have already added one function, now you want to add a second function, you can use append operation or concatenation. And you can clear using without giving any value. So let's try something like, let's set the tracer to, now we have function graph. Let's set function tracer, set it into, we need to write the name of the tracer into current underscore tracer file and validate it. You have function tracer set or not? Yes, you have function tracer set. Now it is currently tracing all the functions which are present in available filter functions. There is no filter set ftrace filter. It is all saying all functions are enabled. There is no particular filter set now. Now I want to set a particular filter. I want to set only kfree. I want to search for functions kfree. I only want to trace kfree. Say kfree ftrace filter. You can now validate by using cat to check whether kfree is set or not. Previously you have seen all functions enabled. Now only kfree is being set. Now if you look into cat trace, it contains the old traces, old information, old logs, and now you can observe only traces being present at the bottom. So it is not deleting the existing logs. It has the existing logs of the functions being called, but the new logs now will only have trace. So this underscore receive message is calling kfree, vfs underscore write v is calling kfree. I can delete this trace. I can remove the current information, like same cases for set ftrace filter. The echo without passing any parameter to echo, write to trace, it will remove the current log. Now if I say cat trace, it only has the new log. So these are the new logs which are present. It only have now kfree because we have set kfree as a filter. Now let's change this and set a different filter. I want to find out all the VFS functions being called. So it also accepts wildcard like asterisk. Let me set VFS functions. I say echo VFS asterisk into set ftrace filter. When I say cat ftrace filter, all the functions which starts with VFS underscore is being set into the filter. Now only these functions will be displayed when you do a cat trace. Let me first clear the trace. Echo trace will clear the existing contents. Now let me say cat trace. And you can observe here, trace is only containing functions of VFS. Gname terminal is calling VFS read, and VFS read is called, the parent function is cases read. This is the system call. System call read calls cases underscore read. Cases underscore read will call VFS read. So let's look into some more, like let's look into do page fault. We know do page fault is the function which is being called when there is a page fault. So let's look into set it to do page fault. Do page fault. Let me do a filter, if trace filter, do page fault is set. Let me clear the trace at the cat trace. You can see there are page faults happening. Genome shell is also creating. This process is also creating page faults. Okay. And let's look into one more, do IRQ. We know what is do underscore IRQ. Do underscore IRQ is a common function to all hardware interrupts. Let's set do underscore IRQ. Do underscore capital IRQ. Let's verify do underscore IRQ set is not. Yes, it is set. Let us clear the trace and cat trace. And you can observe there are interrupts happening here. There are some interrupts which are happening. So like this, you can filter the functions which you want to trace using set ftrace filter function. And if I want to clear this filter, I can simply say currently we have do underscore IRQ set. I can simply say set ftrace filter. Now it will clear the current filter set and you have all functions enabled. So this is one file for filtering. If you enable functions in this file, ftrace will only trace those functions. There is another way, cat trace. You can see all the functions are being traced now. If you do not want a particular function to be traced, you can add that in this file, set ftrace no trace. For example, let's look what is present in this file. Set ftrace no trace. You have no function disabled now. You can disable a particular function. For example, I do not want spin lock underscore anything which has spin lock. Now let me see. Or is it spin underscore lock? Let's see what all functions we have for spin lock. Available filter functions will give you what all functions can be filtered. You have, it is spin underscore lock. You have spin underscore lock. Spin underscore lock calls raw underscore spin lock. Let's disable anything which has spin lock. So let's say this. Let's say this echo anything which starts with spin underscore lock and ends with something. So spin underscore lock is between the starting and ending. I'm going to set it into ftrace no trace file. Let's see what all functions are disabled. These all functions are disabled. Now these functions will not be traced. Let's clear the trace now. And let's search for whether these functions are present in the trace or not. I'm going to do a grep for spin underscore lock. And there is no such spin underscore lock present in the trace. When I clear the no trace file and clear this trace, Now you can see there will be a lot of spin lock functions being called because all the functions are not, no function is disabled now. All the functions are enabled. There is no filter set. So there are two functions for filtering. You have set ftrace filter and you have set ftrace no trace. Also, when you use do underscore IRQ and in the filter and function underscore graph, will give you interrupt times, interrupt latencies of all the interrupts that are happening on your system. Let's try this. So I'm going to say do underscore IRQ in ftrace filter, and I'm going to say function underscore graph in the current tracing. Now I say cat trace. This will give you how much time a particular trace of particular interrupt is taking. It's taking 60 microseconds, 23 microseconds, and you also have the plus, which identifies the duration. So you can find out the latencies using function graph tracer. Just need to set the function graph and set the filter to do underscore IRQ, and you will find out interrupt times. Filters support wildcards like asterisk and question mark. We have seen some of them just now. Value asterisk will select all functions that start with string value. Asterisk value will select all functions that end with string value. If you have asterisk in starting at end, you'll have all functions that start and end with string value. So some of the examples are like echo zen star. So let's try some of the examples. Like we have tried this, but let's try it again. So let me first check what is the ftrace filter. We have do IRQ. I'm setting to zen. Now you have all the things which starts with zen. Even zennet is there. Zen underscore is there. All the functions which start with xen is present here. Then you have star, lock, star. This means all functions which have lock in between. So let's try this. Now let's set the value of anything which has lock, either at the end or in between, or it can be starting as well. You'll be seeing lock is there here. Anywhere, even in block, you have a lock. This have been set. This have been set. Same case is like with mutex. If you want to do a mutex APIs filtering, you can do this. Like you have mutex at the starting, mutex at the end, and mutex in between, mutex at the end. Starting with 4.10, they have been added extended globe matches. Means you have now question mark as well. So when you add question mark, this will change. Let's see what all changes. Like if I say this, now look into ftrace filter, you have only one character here, right? Question mark means only one character. If I remove this question mark, I will not be saying this. So it's an invalid argument because there are no functions. It starts with raw. That's the reason it says invalid argument. But with question mark means it can be any one character. So underscore is there. So that's the reason we have asterisk. You can add asterisk. Asterisk means it can be more than one. But with question mark, it is here you only have some of them which starts with raw. But if you have question mark, it is only one. Asterisk means it can be more than one. Some questions for you. Does available filter functions file, which we have seen, right, will it show only exported symbols or all kernel symbols? One more question is, what happens if there are two functions with same function name? Think for some time. What happens if I have two functions in two different kernel files with same function name? It is possible because each and every function is static to the same driver or same C code. Let's see the answers for this. Every function which is present in call sims is present in available filter function, which means every single function can be traced. every single kernel function can be traced. What happens if we have two functions with the same function name? In this case, it will enable both of them, and you will be seeing both of them in the trace file. I have a simple character device driver, which implements the basic file operations: read, write, open, release. And the implementation is very simple. You have a print statement in each of the file operations. So you're creating mychar dev here. Device name is mychar dev, or it's my device. So you're not passing there, it's my device. And in the user app, you are opening the device, you are writing and reading, you're trying all the file operations. Now let's see whether we can use trace here. So I am compiling this module, loading this module. The module has been loaded. A device should be created. Yeah, device is created. And let's give the permissions for normal user to access. I'm giving 6666 for this read and write permissions. Let's try the user app. Now let's compile the user app and run it. Opening file, write, read, close. And the character driver is working as expected. Now let's verify whether these functions are being added to TraceFS available filter functions or not. So let's search for available filter functions. We have in our code functions like device underscore read, this one, device underscore write, device underscore release, device underscore open. So I'm going to search for device underscore read. Yeah, there's a device underscore read, and you can see there is a name of the module, which is hello in the bracket. Let's search for device underscore write. We have device underscore write also present here. Let's search for device underscore star. Missing a lot of them you have, but let's search which starts with, like, can I use asterisk? Yeah, you can use caret. Caret will make sure it starts with device. Let's change the name, or let's keep it as it is. Okay, so you have device open, device read, write, release, and the module is added. If I remove the module, let's again search for this. They have been removed. Device underscore open, read, write, release, open, they have been removed. Let's add the module again. And they have been added successfully. So all the modules, even when you load some new module, you have them added in the available filter functions. Available filter function file will have the functions which are present in your module. What about, we have also here module init and module exit, like test hello init and test hello exit. So let's try them. Do we have them? Test hello. Yeah, you have test hello init and you have test hello exit as well. So yeah, it's good. So you have our modules. Now what we'll do, we'll try our user app. We'll try the user app now. Let us do sudo chmod. So we are giving read-write permissions for every user here. Now we need to add a filter. Let's add a filter. So currently, let's see, we have this as a filter. And what is a tracer? We have function graph. Let me set function as a tracer, current tracer. I'm setting function as the current tracer. And now I'm setting a filter. I'm setting device underscore open, device underscore close, release, which is not close. We have device underscore release here, device underscore release, device underscore read, device underscore write. Now I'm setting this in not this file, setf trace filter. Let's check setf trace filter is having this. Yeah, you have additional device release, which is, as I said, right, we have discussed what happens if there are two functions which are same name, both of them will be added. You have device underscore release, which is a global function, and device underscore release, which is a function which is provided by hello module. Now let's clear the trace. Let's search cat trace. Nothing is being there. Now let's run the user app. You can see this open file. You have seen this cat ref open, device open. Now there was a write, and then from BFS write, you have observed there is a device write. Now there is a read, BFS read, device read. So these are our functions: device open, device write, device read. This is the parent function. This is the function which is calling this particular function. And if you see the PID, let's see the PID. ESAF if grep 379942. It is user app. So you can see the PID. And we're not sure why it is showing ... but it should be a user app. And finally, when we call close, we have device release being called. So you can observe the flow right now. When I'm calling open, read, write, close, corresponding device open, device write, device read, device release is being called from the kernel space. Let's try function graph. I'm going to set the current tracer as function graph. What about when I change the tracer? Will it remove the current filters? No, the current filters still exist, but it will clear the trace. Let's run watch command on trace. I'm running watch command, continuously calling trace. Now I'm going to run this user app again. You can see it called open, device underscore open is executed. And device write. So this function took 5 microseconds, device open and device write took 5 microseconds and 4 microseconds. I'm calling read, it took 3 microseconds. This function execution took 3 microseconds. And close, it took 4 microseconds. There was a delay because we are running watch for 2 seconds. If you change the watch delay, I can say 0.1, you can say difference, show me the difference. Will not be seeing the delay here. So as I type open, you get open there, right? You have write there, read is being added, close is being added. Let's see whether this duration is working as expected or not. I will add a sleep in the code. Let's add a sleep. So include delay.h. I'm going to include Linux delay.h file. And let's add sleep in read function. I say sleep for 1000 seconds. I'm going to compile this module. Remove the existing module, load this module, queue permissions. I'm running the user app now. Open, it took. So let us clear the trace. So as the module is removed, you can see the filter should be removed. That's the reason you are not seeing the trace output being added. So the filter is removed when you remove the module. We need to add it again. So let's add it again. Now let's run cat trace, read. It took 1 millisecond. What we have given took not 1 millisecond, it took more than that. So you can see dollar there means it took 1 second. 1 second is, yes, we have added a mslib of 1000. That's the reason you have 1 second here. So 1 3, yeah, it's 1 second. So the duration changes if depending on how much time your function is taking. So this is how you can trace your own module. If you have your kernel module, you can add it into set ftrace filter, and then you can work. So let's try one more use case. I'm going to remove the module, and I'm going to add, let's see the filter. I do not have anything in the filter. And when I'm going to add the functions which are not listed, this will throw me an error because these functions are not present in available filter functions. This is how you can debug, add, or verify what all functions are being called whenever some of your system call may not be executed of your file operations in the character driver. You can use ftrace and verify whether your function in the kernel is being called or not without adding any print k. Suppose you only want to trace what is happening when you run a specific test and do not want to run once the test is completed. In this case, you can use tracing_on file. Tracing_on file is a on-off switch to make the ring buffer writable or not. If you say echo 0 to tracing_on, it will disable writing to the ring buffer. But everything else still happens with the traces. All the functions of traces are still being called. Just the ring buffer is not recording. It will not attempt to write any data. All the functions related to traces are still performed. To re-enable the writing to ring buffer, you simply need to write a 1 into the file. Example scenario which can be like, you disable the tracer, you set the current tracer, which is function graph, you enable the tracer, run a test, and you disable the tracer. This will narrow the data stored by function graph tracer to include mostly just the data accumulated by this particular test application. Try this. Let's try this. We have all functions enabled. What is the value of tracing on now? Tracing on is 1 means you're allowing writing to the ring buffer, and you have the content in trace continuously being added because there are no filters. Now I'm going to write 0 to tracing on. This means you are disabling writing to the ring buffer. You are disabling the recording. Now you will see the content is still present. This is the previous content before you actually disabled the recording. So if you clear this, there is no content now. No content now because you have disabled tracing. So if I can enable it by just writing 1 to tracing on. Now when I say cat trace, trace is started and it is continuously writing to the ftrace is continuously writing to the ring buffer. So very useful file if you want to only narrow down, do not want to record all the functions, must want to record functions when this test is particularly executed. So enable the tracing, run the test, disable the tracing. Ftrace, as discussed, it internally uses a ring buffer of fixed size. If I want to find out the size of the ring buffer, there is a file which gives us that information. Buffer_size_kb. If this buffer of this particular size is full, then ftrace framework will start overwriting the existing tracing information. So let's look into the size. You have buffer size kb. So buffer_size_kb is 1408. So 1408 kb is the size of ring buffer. Now we know to read this ring buffer, we are using trace file, but there is one more file by which you can also read the content of the ring buffer. It is trace underscore pipe. What is the difference between trace and trace underscore pipe? The difference is trace is a non-consuming read. When you read this file, it will pause the tracing, whereas trace underscore pipe is a consuming read. It does not stop the tracing when you are reading this file. Each time you read the contents of the trace file, it will print the same tracing entries, whereas with trace underscore pipe, each time you read the file, the data is consumed, and the next time you read, data will be different, and also trace underscore pipe will block for the data to come, whereas trace is not blocking. It will not block if there is no data. It will just print and exit. There is no blocking there. So let's try. So we have current tracer function graph, and trace is continuously being executed. Now what I will do is I will disable the tracing. I'll say disable writing to the ring buffer. Now I call trace and it will print me information. I call trace again, it will print me the same information. You say head minus n20. We'll see alloc underscore set underscore pt is the first function. Again, alloc underscore set underscore pt is the same function. So if I now call trace underscore pipe, it is reading the same information, but it is consuming that information. Now, as there is no information, because it has already consumed, it blocks. But when there is an information, it will not block. It will print all the information and exit. So as we have disabled the tracing, it is blocking. Now let's enable the tracing. So trace underscore pipe is consumer, and it will consume and it will print. I have enabled the tracing. Now trace underscore pipe is continuously being printing. It is not stopping like trace because it is consuming it, it's printing it, consuming it, printing it. Whatever information is coming, it is consuming it and it is printing it. Whereas when you do trace, it is a non-consumer. It will just print, and whenever you are calling trace, the recording is stopped. So this is an important point. Recording is stopped or paused when you are using a trace, but information is not removed from the trace file. Information is removed or consumed from the trace buffer, the tracing buffer, but it does not stop the tracing. This is very useful information if you whether you want to use a trace file or a trace underscore pipe. Filtering, function graph tracing. So we have already used some of the filter files, like we have used set ftrace filter, set ftrace no trace. This was applicable to both function tracer as well as function graph tracer. But there is one more file which is set graph function, which is similar to set ftrace filter, but this is only applicable to function graph tracer. Functions which are listed in this file will cause the function graph tracer to only trace this function and the function that they call. What is the benefit of this file? It is useful to find out what calls are made by a kernel function. For example, if I want to find out what calls are made by this function vfs underscore read, I can simply use this particular set graph function file. For example, let's try to find out. I want to find out. First, let's check the current tracer. It is function graph and tracing is on. It's enabled. I can disable the tracing and I can clear the buffer. Now I do not have anything here. I have disabled the recording. Now I can use echo. I can say VFS read. What all functions are being called by VFS read? I just want to know what all functions are being called by VFS underscore read. I write in set graph filter, set graph function. So we have set ftrace filter, then we have set graph function. Let's validate set graph function. We have VFS read added. We have to enable tracing now. So I'm going to enable tracing by writing to on. Check it as now check. So each time VFS read function is being executed, all the functions which are called by VFS read will be logged in the FS trace. So let's try. So VFS read is calling RW verify area, this function, and this function is calling security file permissions. So till now this is this function. Then you have FS notify. This is RW verify area. This is whole RW verify area, which internally calls VFS read underscore VFS read. So till this is all VFS read. You have RW verify area, you have underscore VFS read, then you have FS notify. This way you can find out what all functions are being called by a particular kernel function. Very useful set graph function. Useful to find out what are the calls made by a kernel function. Let's try our kernel driver. We have a kernel driver here. Let's verify we have this added. Now we have to add this module. Now I have this added. Let me give permissions now. Let's change the filter. I have to add echo. VF device open. Instead of writing to ftrace filter, I write it to setGraph function. Now let's verify the content of setGraph function. We have this. Now let me clear the trace. We should have disabled the tracing. Anyhow, we have cleared the trace. Now let's use, instead of trace, I use trace pipe. Let's see what happens now. Let us run the user app. And you can see a lot of functions are being called. So device underscore open. There was an interrupt in between. So this is an interrupt. There was an interrupt when device underscore open called. Interrupt got completed here. So this opening arrow, we'll be looking into this. Then there was a print k, and print k is calling a lot of functions. You can observe here. Device underscore open and print k. Finally, we have again schedule. There was a schedule. There was some schedule, and that got executed in this duration. There was some context switch happening. And let's say we call write. There was a device write, and there was some interrupt again, and there was a print k. Read close. We have device read. Then we have print k. Then we called msleep, and you can see we have msleep here. Very useful, right? No need of adding print case of what all functions are being called. You can simply use ftrace graph, no function, and we can see what all functions are being called by our file operations. Revise, release, and print k. Finally, that's it. So this is how you can use set. Then we have another one, which is set graph no trace. This is an opposite of set graph function. This will disable function graph tracing when the function is hit until it exits the function. So it's like set graph, set ftrace filter, and set ftrace no trace. Ftrace, it also allows you to trace a specific process. For example, you have a scenario. You want to trace all the system calls, all the kernel functions made by a particular process. Yes, it is possible by using ftrace. Ftrace has a file set underscore ftrace underscore PID. Just need to echo the PID into this file. So important here, not process name, it's a PID. So you just need to echo the PID in set underscore ftrace underscore PID file. This is one way, like you disable the tracing, you enable function tracer, and now you are using a shell. You're running this command in this shell. Echo dollar will give the name of the, it will give the process ID of this shell, and one will enable the tracing, and you are executing that particular command. And then you can disable the tracing. For example, this is one example, like echo dollar dollar is giving the, so if you say echo here, if I say echo dollar dollar, it will give me the PID of this shell, which is this PID. Stop this. So let's try to execute this. Let's say we are disabling the tracing. I disable the tracing and I clear the trace. I set function as the tracer. I am verifying the functions which are set. Let me clear this set graph function. Let me now let's see what all let us do a set on the stress filter. All functions are enabled, and now I'm going to run this command. And then we'll say disable tracing. So what we are doing here, we are setting the PID of this shell, and we are enabling the tracing, executing echo hello, and disabling the tracing. Running this command, hello got executed. The tracing should be off now because we have finally disabled it. Now it is on. What about the ftrace PID? It has set the PID. And then you have the trace file. This now trace only contains the functions of those PID 38, 35, 16. It is only having those functions executed by that particular PID. You can see we just said echo hello, executed echo hello, but you can observe how many functions we have. We have lot of functions. Sorry, yes. We have lot of functions executed in the kernel space when you just said echo hello. So using set ftrace PID, you can just set a particular PID and trace calls related to that specific process. For example, we have a script here. traceme.sh. This script first gets the location of debugfs. So as I said, tracing folder is also present in debugfs. So this grep will give me the location of debugfs. We are first setting no operation tracer, clearing the trace file, then executing whatever command which we are passing, whatever argument we are passing to this script, then setting the ftrace PID, setting function as a current tracer, enabling the tracing, executing that particular command, and disabling the tracing. Let's try this script now. So I need to be in sudo. I say traceme.sh ls. So ls got executed and you have ls output here. But now in the trace, you can see all the kernel functions for this particular ls command is present now. A lot of kernel functions are present for this ls command, and you can observe the PID is the PID of that particular process which executed ls. We have started a new shell, and then what we did is we executed in that shell this ls command. The other way is you can use filters. You can have filters as well. So here in this example, the only difference is I've added vf underscore into set ftrace filter. Now when I say set f trace me with filter.sh ls. It executes ls, prints the output of ls. Now let's see this thing. You do not have any VFS because you're just calling ls. That's the reason you do not have VFS there. But if I say echo hello, hello got executed. Now you have some VFS functions because you're trying to do an echo which will use VFS filters. So this is a useful thing, tracing a specific process using setftrace PID. Like we have setftrace PID, which allows you to trace all the functions related to a specific process. Ftrace also provides you a way to trace all functions related to a specific module. For example, if I want to trace all the functions from Ethernet driver, the Ethernet driver which I use is LSPCI. I did this is my Ethernet controller, the kernel module which is E1000. So and this is a module on my system. If you grep for E1000, it's a module. Suppose if I want to trace all the functions called into this module, I can simply use this syntax: colon, mod says module, colon, and name of the module. So let's do this. So instead of doing this, I have the script already present for me, which performs the same operation. So here I have this set into the filter. So I'm clearing the trace, I'm clearing the PID, do not want any PID to be present. I'm setting the function as the current tracer. Then I'm setting this as a filter, which will read this module and what all functions present in this module, and will set in the filter. And then I'm enabling the tracing, and I'm just waiting for user to press enter. What we can do is we can add disabling tracing here. I'll disable the tracing first and then do this operation. So let me run this sudo traceme.sh. Now it is waiting for my enter. Let's see the content of setftrace filter. It has all the functions of E1000 module. So this all functions of E1000 module are present here. Let's look into cat trace. Do we have some functions being called? Yeah, there are some functions which are being called in cat trace. Let's use cat trace pipe. So now what we'll do is we'll down the interface. We'll say interface down. We have this interface here, ENP0S3. We'll down this and see whether functions in this module are being called. I need sudo here. I'm just pressing enter. And a lot of functions are being called here. You can observe here. When I said down, a lot of functions have been called. Like there are some E1000 down, E1000 close, etc. Now when I say up, again, a lot of functions are being called. A lot of functions are being called here again. So this way, we can trace all functions of a specific module. We need to use this syntax. You have colon, mod, colon, and then you just append this into, not append, just need to use the redirection operator. And this will have all the functions related to this module added into the ftrace filter. Trace underscore print k. Like we have print k, which is king of all debuggers. We have trace underscore print k. This is being provided by ftrace. So what is the difference? Print k, it is a king of all debuggers, but it has some problems. You cannot use print k in interrupt context, such as timer interrupts, scheduler, network. This can create a live lock. Sometimes you have observed bug disappears when we add few print k's if something is time sensitive. And print k, when you are trying to write to a console, it will take several milliseconds. That's the reason a new print k is being provided by ftrace. It is trace underscore print k. Writing will be in the order of microseconds. When you call trace underscore print k, it will just write to a ring buffer. It will not write to a console. And this way, this can be used in any context, interrupt context, scheduler, NMI, etc. And you can read it via trace file, not dmessage. When you use trace underscore print k, you need to use trace file. What is the advantage here? Performance. It will allow you to record the most sensitive areas of the kernel with very little impact. So how can I use it? Just need to call trace underscore print k. Instead of using print k, you say trace underscore print k. It does not have any log levels like print k. So you need to remove the log levels if you are just having any log levels. If you are converting print k to trace underscore print k and they have log levels, then you need to remove them. So trace underscore print k, it will appear in any tracer, either it can be a function or a function graph tracer. I have a simple module which is actually trying to use trace underscore print k. So here you can observe I have a simple module. I'm using request underscore IRQ. This is used to request keyboard IRQ, IRQ1, keyboard IRQ. In the interrupt handler, I'm using trace underscore print k because as this is just writing to the ring buffer, I can use it. Does not have any impact. And I'm writing what is the character which is being pressed and released. So let's see how this works. I'm going to load this module. Let us first, what we'll do, we'll clear everything. I will clear first disable tracing on. I have disabled tracing on. Let me clear trace. Let me clear ftrace filter. Now we have all the filters enabled. What I'll do is I'll set no. Let's see if I set no operation, whether we have trace print k working or not. The current tracer is no operation. I'm using trace underscore pipe, which will block for me. Now I will load this module. I'm loading this module. There is already a same name, so let's remove this. Nothing is being k. I pressed some keys, nothing is happening. So what I will do is I will set function as the current tracer and I press ls and I say cat trace pipe and I say ll, nothing happens. So let's verify what are the problems we have here. Let's check you have any filter. All functions are enabled. What is the current tracer function? Whether you have any PID. No PID is set. And you are using trace. Nothing is being added. So what is the problem? Why is trace underscore print k not working? So you can observe here trace underscore print k being used, allocating extra memory. This means this is a debug kernel and it is unsafe for production use. You got this particular log. I'm pressing something and something is missing here because it is not as all the functions are enabled. It should start tracing those functions. Let's see whether we have. Why is this not working? Let's understand it properly. No trace, no functions disabled. Not sure why this is not working. Tracing. Okay, let's see whether we have tracing on set or not. We have tracing on disabled. This is the reason it was not working. Let us enable tracing on. And let's see. NOP current tracer. Now we have say trace underscore pipe. And you can observe here, we have this working. I type J, I type K, I type L. So trace underscore print K, it works with no NOP tracer. It works with a function graph, all the traces. So very useful, and it does not add much delay. It just writes to the buffer, and you can use trace file to read it. So if you have some performance or sensitive areas where the frequency is low, you can use trace underscore print K instead of print K. Finding kernel functions which are taking greater than 10 milliseconds. So if you want to find functions which are taking greater than 10 milliseconds, you can use a file known as tracing underscore threshold. So there's a file in tracefs, which is tracing underscore threshold. Using this file, you can find out kernel functions which are taking greater than 10 milliseconds or more than whatever time you want. So this file, ftrace uses this file and it compares the function duration. If it is greater than the value present in this file, it will log tracing entries in the ring buffer. By default, the value is 0. This means ftrace is not carrying it. So by default, it's 0. It means ftrace will not carry this particular file. But if I write some particular value, then ftrace will validate whether the function duration is greater than this value. If it is, then only it will log it into the tracing file. So if I want to find out functions which are taking greater than 10 milliseconds, you can just say echo 10,000. So now it is 10 milliseconds. This is micros and this is 10 milliseconds. Now if I say cat trace, so let us first set the tracer to function graph. I'm going to set the tracer to function graph. Now let's see the trace files. Trace file now only contains functions which are taking more than 10 milliseconds. This is taking more, like 309 milliseconds. So now with ftrace, you are able to find out you're only logging the functions which are taking more than 10 milliseconds. Here you can see schedule is taking 225 milliseconds. Do nanosleep is taking 25 milliseconds. This way you can find out what all functions are taking more than 10 milliseconds. Whatever the value, like this function takes it in microseconds. The unit of this particular is in microseconds. And if you set back to 0, ftrace will start tracing all the functions. Now you can see all the functions are being traced. Finding out how user space code is getting into kernel, which is a function which is called when the user space tries to enter the kernel. You can find out using max underscore graph underscore depth file. This particular thing can only be used with function underscore tracer, function underscore graph tracer. Max underscore graph underscore depth file, it contains the maximum depth it will trace into a function. By default, the value is 0. This means unlimited depth. Max underscore graph underscore depth. So it's 0. This means you will be having unlimited depth. Now if I set echo 1 to max underscore graph underscore depth, this will only trace the first function and will ignore the other functions. I'm going to set this to 1. Now let's say cat trace. Let us first clear this so you will not be seeing the existing entries. So this say trace underscore pipe. So you can observe here do underscore syscall underscore 64 is a function which is normally being called when system call is being executed, and there is some other functions which are being executed, but for processes, user space processes, do underscore syscall underscore 64 is the first function through which the user space code gets into the kernel space. If I set echo 2 to max graph depth, then I will be finding out the next function after do syscall 64. So let me set echo 2 and we'll say cat trace now. Now you will be seeing the next function which is being called after do syscall 64. It is x64 sys underscore receive message. Do page fault is calling underscore underscore do page fault. Now we have set the max graph depth to 2. This is the reason you're seeing two functions. If you set to 1, it will have one function. If you set to 3, you have 3 functions. Like here you can see there was someone was calling open it. That's the reason it is being displayed here. Very useful one. This do max underscore graph depth.